So let's start. Let's start there. Let me show you the question. Right. Are you able to see the question? We were discussing 2006 matter and radiation question. 2006 matter and radiation question. This one. Am I right here? So here we have answered up to simple, Roman number 3 we discussed, Roman number 4 we discussed. We want to discuss Roman number 5. Roman number 5. So that's what we want to discuss today. That's what we are going to discuss today. Right. So can somebody read Roman number 5? Unmute the mic and read Roman number 5, please.
The kinetic energy K of the emitted alpha particle is given by K equals AD divided by AD plus A alpha E, where AD and A alpha are the mass numbers of the daughter atom and the alpha particle respectively. Find K.
Thank you, Ria. Thank you very much. Right, they have given us an equation in Roman number 5. The given equation is the kinetic energy K of an emitted alpha particle is given by the equation kinetic energy of an alpha particle K equals A simple D divided by A simple D plus A alpha times capital E times capital E. They have said that we are AD and A alpha are the mass numbers of daughter atom and the alpha respectively and alpha particle respectively and the alpha particle respectively. Find K. Right. The equation, they have given us this equation. What is the equation? Here, a polonium 210 atom, right? A polonium 210 broken into two particles. The first one is 206, that is lead Pb, plus alpha mass number is 4, and we get some energy. This is the equation. This is the equation that they have given. Here, capital E is the energy created due to this energy loss. It means if you take the mass of the polonium atom, that will be mass of the polonium atom is greater than the summation of the masses of all these things at the right hand side, lead atom and alpha particle. It means some mass is reduced due to this reaction. Some mass is reduced due to that reaction. The reduction of mass is converted into energy. That energy can be calculated by this equation, right? And last week we have calculated that energy. Somebody please tell me the amount of energy created due to this reaction. Somebody please tell me the amount of energy created due to this nuclear reaction, capital E. Last week we found this here. Please tell me, dear.
8.4006
10 to the power
minus 13. Minus 13.
Minus 13 joules. So this much of energy is created due to this reaction. Here, this K, listen dear, this K is the kinetic energy of the alpha particle. Got it? Right. AD means mass number of daughter atoms. Daughter atom means this. This PP206 is said to be the daughter atom. Polonium 210. Polonium 210 is said to be the mother atom. Normally we don't use the term atom, we normally use nucleus. Mother nucleus, daughter nucleus. But here they have used the term atom. Right? So these are the given things for us to find the value of K. Right? So first of all, please write these things for the Roman number 5. First of all, write these things for the Roman number 5. Everything that I have written on the board. Then you can get a clear idea about the question. After that, let's calculate the value of the K. Start here. Please, quick. Shall we calculate the value of the constant area, Lamai? The kinetic energy of the released alpha particle is given by this equation. Here, AD is the mass number of daughter atom, that is 206, divided by this. AD, again the mass number of daughter atom, 206, plus mass number of alpha particle, that is 4. The number which is kept on the head is the mass number, that is 4, into E. E is 8.4 into 10 to the power minus 13 joule. 10 to the power minus 13 joule. Right? Now we can simplify this. Let me write the equation mark here. 206 divided by 206 plus 4, 210 into 8.4 into 10 to the power minus 11. Got it? Can you see the board? Yeah, let me. Now okay, right? Now okay. This can be simplified like this. You see, 210. Let me write this like this, 206. I will not do anything to this 210. But 8.4, let me write 8.4 as 840. Then 10 to the power minus 11 will be, somebody unmute the mic and tell me. If I convert 8.4 into 10 to the power minus 11 as 840, what will be the power of the term 10? Somebody unmute the mic and tell me. Tamai? What should be the power of this 10? Think and tell me. Can you hear me? Lamai, can you hear me?
Yes, sir.
Sir, can you repeat the question?
Can you hear me?
Yes, sir.
So then
Yes,
tell
sir.
me the power of 10.
Minus 15.
Minus,
15.
I can't hear. Speak loudly. Minus
15, sir.
15.
It's minus 13.
Sir, the initial value
Minus
is 8.4.
30. You see, I have taken only 2 decimal places. 1, 2. So minus 11
So it
will
was
be
minus
minus
13, sir.
30. Only 2
Sir, the initial value was
zeros
minus
are taken
13.
that side. So it will be minus 30. What
So
is
it
the
was minus
advantage of writing like that? What is the advantage of writing 8.4 as 840? The advantage is this, you see, I can write this 206 multiplied by, let me write it here. The advantage is 206 multiplied by 840 divided by 210. This 0 and this 0 cancelled out. 84 divided by 21 is 4. Got it? Into 10 to the power minus 30. So that's the advantage of writing 8.4 as 840. Once you write 840, 0, 0 cancelled out. 84 divided by 21 is 4. Now so simple. Let me simplify this. 4 times 6 is 24. 2 remaining. 4 times 0, 0 plus 2 is 2. 4 times 2, 8. Into 10 to the power minus 13 joule. But we do not keep the answer like that. Earlier, I have taken decimal point to the right hand side. Now I'll take decimal point to the left hand side. So then the final answer will be 8.24 into 10 to the power minus 11 joule. Minus 13 will be minus 11 once you take 2 decimal points to the left hand side. Who got this answer at home, dear? Who got this answer at home? Anybody in the class? Lamai?
Excuse me, sir.
Yes, I'm listening.
Sir, initially, sir wrote that the energy is 8.4 into 10 to the power 13. But down the line, sir said that it's 8.4 into 10 to the power 11.
Yes. Did you notice it? 10 to the power minus 13 has changed to minus 11. That is impossible. Sorry. 10 to the power minus 13. Sorry. Thank you, Buddha. Minus 13. There was a writing mistake. This should be 10 to the power minus 13. So once you take 2 decimal points to the right hand side, minus 30 should become minus 15. Thank you. Minus 15. So then 8.4 into 10 to the power 8.4 into 10 to the power minus 13. Here this is 10 to the power 13. Thank you. So minus 13 will be minus 15 when you take 2 decimal points to the right hand side to make it 840. So this is minus 15. Thank you, Ula. This is minus 15. So this will still be minus 15. Once you take 2 decimal point to the left hand side, minus 15 will be minus 13. Yeah, thank you. So final answer is 8.24 into 10 to the power minus 13. Who got this answer at home? I think I have corrected the mistake. Thank you, dear. Who got this answer at home? Anybody in the class? Right, shall we go to next question, dear? Now, shall we go to next question?
Okay, sir.
Okay. Right, let me show you the next question. That is, we have answered up to Roman number 5. We should answer now Roman number 6. Right. Somebody please unmute the mic and read Roman number 6. Start.
A radioactive sample contains 1 gram of polonium. Decay constant of polonium for the decay in Roman number 1 above is 5.6 into 10 to the power minus 5 per second.
Under that, they have asked several questions. Thank you, dear. Under that, they have asked several questions. Roman number 6. Under that, they have asked several questions as A, B, C, D, E, F. Question simple A. Find the following. The initial number of polonium atoms in the sample. Take Avogadro's constant as 6 into 10 to the power 23 per mole. I should explain what the Avogadro's constant is. Before that, let me read Roman number 6 once again. Let me read Roman number 6 once again. Right. Now you are able to see Roman number 6 and simple A both. A radioactive sample contain 1 gram of polonium. The decay constant of polonium for the decay in Roman number 1 is 5.6 into Roman number 1 means the given reaction. For the given reaction, decay constant is 5.6 into 10 to the power minus 8 per second. So they have given only 1 gram of polonium. Question asks the initial number of polonium atoms in the sample. And they have given us a number which is called Avogadro's constant. So let me explain all these things. Let me explain all these things given in Roman number 6 and simple A. Because there may be some students who may have not learned these things. Because there are some students who have not learned chemistry. So let me explain. Right. If you have not written the things that I have written on the board yet, please take a screenshot. Because I need space to explain the things. If you want any more space, please take a screenshot. If you want any more time to write the things, please take a screenshot because I'm going to erase everything. Right. Now, first of all, I should explain Avogadro's number. Avogadro's number is something like this. Right. Look at both. So this is the given reaction. In this reaction, this 210 is said to be the mass number. What is mass number here? Mass number gives the summation of the number of protons and the number of neutrons in the sample. So this is the summation of number of neutrons and number of protons, right? And here we write the number of protons here. Somebody please tell me the number of protons in a polonium atom, dear. Somebody unmute the mic and tell me. I have given it. Lamai. Just look at, read your ear note and last week note and tell me the number that I have written here and the number that I have written here and the number that I have written here.
Polonium is 84.
92.
The atomic the
92.
atomic number is 84, sir.
Lead. Ayyo. So it means you have not written the notes, Neil. You have not written notes, that's why you can't tell me those numbers.
Sir, 84.
Lead. Is lead 84?
82, sir.
82. Then alpha?
2.
2. There are 2 protons in alpha. There are 82 protons in the nucleus of a lead atom. There are 84 protons in a polonium atom. Check these numbers there. 84 protons in the nucleus of a polonium atom. 82 protons in the nucleus of a lead atom. And there are 2 protons in the alpha particle. 2 protons and 2 neutrons. Right. This is called mass number. This 210 is called mass number. Mass number. Right. The magic of the mass number is this. If we take 210 grams of polonium, right? There will be 6 into 10 to the power 23 number of polonium atoms. This is the magic. What's the magic of the mass number here? If we take 210 grams of polonium, there will be this much of 16 to 10 to the power 23 number of polonium atoms. This number is called the Avogadro's number. Avogadro's number. Right. Normally, the real value of normally in our theory notes we normally write Avogadro's number as 6.022 into 10 to the power 23. But here we have to use the value which is given in the exam. We have to use the value given in the exam, and it is usually use 6 instead of 6.022. Right. And if we have this much of atoms, if we have 6 into 10 to the power 23, it means actually this is the Avogadro's number. If we have 6 into 10 to the power 23, number of polonium atoms, this much of polonium atoms is said to be 1 mole of polonium, 1 mole of polonium. This is the theory. What are things here? This 210 is the summation of number of neutrons and number of protons in the nucleus. If we take 210 grams of polonium, right, there will be 6 into 10 to the power 23 number of polonium atoms. This 6 into 23 is said to be the Avogadro's number. The accurate value of Avogadro's number is 6.022 into 10 to the power 23, but we use the value given in the examination. If we take Avogadro's number of atom, it means if we take 6 into 10 to the power 23 number of polonium atoms, that is equal to 1 mole of polonium. So I would like if you write these things again for the Roman number 6. I know that you have written this equation earlier again, but if you write these things, it will help you to understand. It will remember, it will help you to memorize the things. You have to remember these things. Therefore, write all the things that are written on the board for Roman number 6. Then we can easily start answering the question Roman number 6. Start here, write them all. Please write them all. Right, so let's write a few statements that will help you to understand. Let's write few statements. Look at board. The mass number of polonium, that is 210. Mass number of polonium 210. Therefore, the mass of 1 mole of polonium. Therefore, the mass of 1 mole of polonium is 210. Please write the unit carefully, gram. Please write the two statements here, quick. Write the two statements. Right, how much gram do we have here? To make 1 mole, we need 210 grams. So it means I can write, so this is the first time that you are doing this kind of equation. That's why I'm writing statements. Otherwise, no need to write this much of statements. Right? So it means the inverse is, right, 210 grams of polonium equal to 1 mole. So therefore, 1 gram of polonium should be equal to, can somebody unmute the mic and tell me? If 210 grams of polonium equal to 1 mole, if we have 1 gram, what will, how many moles will be there? How do we find? What's the procedure?
1 over 210.
Right. The mass number of polonium is 210. Therefore, mass of 1 mole of polonium 210 grams. So, if we take 200 grams, 210 grams of polonium, there will be 1 mole. So, if I want to find the number of polonium moles in 1 gram, so to obtain 1, I have divided 210 by 210. This will be 1. If I divide 210 by 210, we will get 1 gram of polonium. If I divide this side by 210, the other side should also be divided by 210. So now we have this much of polonium moles. And the other statement is number of polonium atoms in 1 mole. Number of polonium atoms in 1 mole is equal to the Avogadro's number. Avogadro's number is given in the question as 16 to 10 to the power 23. Right? So there will be this much of atoms in 1 mole. But do we have 1 mole? That's the question. Do we have 1 mole of polonium here? Lamai? Do we have 1 mole of polonium?
No, sir.
No. How many moles do we have?
1 over 210.
1 over 210. So thank you, Buddha. So let's find the final statement. Therefore, the number of polonium atoms in 1 over 210 moles. Can you understand it? In 1 mole, we have this much of atoms. Therefore, number of atoms in 1 over 210 moles is 1 over 210 should be multiplied by 16 to 10 to the power 23. So now we can easily simplify this. Look at board. This 6 into 10 to the power 23. 1 into 6 is 6. 16 to 10 to the power 23 can be written as 600 into 10 to the power 21. Can you understand that, Maxi? 23 by taking two zeros of 10 to the power 23, it will be 600. Then 10 to the power 23 will be 10 to the power 21 divided by 210. Now this 0 and this 0 cancelled out. We can easily divide this 60 and 21. What's the method here? 60 divided by 3 is 20. 21 divided by 3 is 7. Am I right? 3 times 20, 60. 3 times 7, 21. Multiplied by 10 to the power 21. So we have this much of polonium atoms in 1 gram of polonium. Please write all the statements. If you have any further doubt, please ask. I can help you. Start there. So finally, let's write that therefore the number of polonium atoms in 1 gram of polonium. The number of polonium atoms in 1 gram of polonium equals 20 divided by 7 into 10 to the power 21. Let me divide this. 20 divided by 7 is 2 divided 20 divided by 7 is 214. 6 remaining. 60 divided by 7. 7 times 7, 49 plus 7, 56. It means 8. 56, 4 remaining. 40 divided by 7 is 5. 35 like that. So 2 decimal points enough. 2.85 into 10 to the power 21. So in the examination, you have to divide and keep the answer like this. But when you substitute this answer, always use the fraction value as 20 over 7. You divide and give the answer with 2 decimal places. But when you want to use this value somewhere else, use the fraction 20 over 7. Complete this. Who got this answer up to 2 decimal places? Anybody in the class? Lamai, who got this answer? Lamai, shall we go to the next question? Shall we go to the next question, Lamai?
Okay, sir.
Okay. Right, let me show you the next question. Right, somebody please unmute the mic and read simple B question. Somebody please read question simple B.
The initial activity A of the sample A equals lambda n.
Thank you, dear. Unfortunately, they have given the equation, so I don't like this. They must not give you the equation. You should remember the equation, but here they have given you the equation. What is activity? Do you remember what the activity is? Anybody in the class? If you remember, please tell me what the activity is. Somebody?
The number of nuclei decay per unit time or the rate of decay.
Very good. Again, dear, for all of us, please tell again.
The number of nuclei decay per unit time or the rate of decay.
Very good. Excellent. I'm so happy with it. Very good. So here, look at board here. Look at board. The polonium converts into lead. So actually we are interested in the nucleus. So this process is said to be decay. This process is said to be decay. If you have enough space on the previous equation, please mark. The converting one atom of one element into an atom of another element, converting an atom of a certain element into an atom of another element is said to be decay or broken. Number of atoms or number of nuclei decay per second is said to be the activity. What is activity here? The number of mother atoms or mother nuclei decay per second is said to be the activity. But we don't use the term second, we use the term rate. The rate of decay of mother nuclei is said to be the activity. There is a law which is called the law of radioactivity. Activity is normally indicated by A. That law of radioactivity tells us activity directly proportional to the number of mother nuclei in the sample. What's it? The law of radioactivity tells us the rate of decay activity directly proportional to the number of mother nuclei or number of mother atoms in the sample. So A directly proportional to N. To convert this directly proportional mark into an equation mark, this side is multiplied by a constant, lambda. Here, lambda is not wavelength. Here, lambda is called decay constant. What's the name of this lambda, everybody? Lambda is known as, everybody, Lamai? Yaku, මොකද්ද lambda කියන්නේ?
Decay
Right?
constant.
Anybody? If not, class is over, right?
Decay constant.
A decay constant. You must be able to see decay constant. What is lambda here? Everybody, once again.
Decay constant.
Other only or any other students? All the students in the class. What is lambda?
Decay
constant.
constant.
Decay constant.
Very good. You should not sleep, right? So they have given everything that we want. They have given everything that we want, right? We should find the activity. They have given lambda. Can somebody tell me the value of lambda? It's given in the question. Somebody please tell me the value of lambda. It's given in the question. Sometimes you may not have the printed version of the tube. Okay. The value of lambda is 5.6 into 10 to the power minus 8. 5.6 into 10 to the power minus 8 per second. Number of atoms decay per second, broken per second is 5.6 into 10 to the power minus 8. N, this is the most important thing. N is the number of polonium atoms in the sample. Somebody unmute the mic and tell me the number of polonium atoms in the sample. Somebody please unmute and tell me the number of polonium atoms in the sample.
21.
Could you please
2.8
speak loudly,
into
dear?
10 to the power 21.
Again, I didn't hear. Sorry.
2.8 into 10 to the power 21.
Very good. This one.
2.8 into 10 to the power 20.
Very good. Thank you. Sorry, my it means sometimes speed is not working. 2.85 into 10 to the power 21. Remember that never use this value for capital N, because this is not exactly, this 2.85 is not exactly equal to 20 over 7. So therefore, whenever we want to use this value, use the fraction. What is the fraction value here? Fraction is 20 over 7 into 10 to the power 21, right? Instead of this number, never use 2.85 into 10 to the power 21. Then simplification will be difficult, and at the same time, you will not get the correct answer. So please write down everything like this and try to simplify this. Write everything and try to simplify and tell me the activity. Capital A is said to be the activity. Do it yourself here. Do it yourself without my help. Start quick. Right. What is the easiest way to simplify this? What is the easiest way to simplify this? 5.6 can be written as 56. Then minus 8 will be minus 9. Simple. 5.6 is written as 56. Then 10 to the power minus 8 will be 10 to the power minus 9. Into 20 over 7 into 10 to the power 21. Now 56 and 7 can be cancelled out. So 7 times 8 is 56. Into 20, I write 10 to the power minus 9 here. I write 10 to the power plus 21 here. Now let's simplify it. 8 times 2, 16, 116 into minus 9 plus 21. That is 10 to the power 11. 10 to the power 11. Let me take 2 decimal points like this, then 11 will be 13. So you will get 1.60 into the 10 to the power 13. The unit of activity is becquerel. Unit of activity is becquerel. Number of atoms broken per second,
About
or
14, sir.
number of atoms decay per second is this activity. Who got this answer? Who got this answer?
10 to the power
1.6.
14.
10 to the power 14.
Sir, 10 to the power 14.
How? Minus 9, 12. This is 12. Minus 9, yeah. 11, 12. So this is 10 to the power 12. Then 12, 13, 14, yes. So this is 10 to the power 14. Who got this answer? Who got this answer? Anybody in the class? Very good. Darwin, shall we go to the next question? Shall we go to the next question, dear?
Okay.
Right. Question A completed. Roman number 6 simple A completed. Roman number 6 simple B completed. Now we should go to simple C. Somebody unmute the mic and read simple C question. Quick. Somebody please read simple C question.
The initial rate of emission of alpha particles.
So it is, thank you, Buddha. It is asked us to find the initial rate of emission of alpha particle. How many alpha particles are released for the decay of one polonium atom? How many alpha particles are emitted when a single polonium atom is broken, when a single polonium atom decays? Somebody?
One alpha particle.
One, yes, dear, one, exactly one. You see this reaction? See the equation you see? A single polonium atom give a single alpha particle. See? One polonium atom, one alpha particle. So for simple C equation, please write an equation statement for simple C. Number of polonium atoms. Sorry, number of alpha particles. For C, please write the number of alpha particles given out due to a decay of number of alpha particles given out due to a decay of a single polonium atom is one. Am I right? Please write this here. Actually, we don't write this kind of statements in the examination. you can directly write the answer. If you directly write the answer, they will give you full marks. But here we write this kind of statements for us to understand, for you to understand. Right. The number of alpha particles given out due to a decay of a single polonium atom is 1. One polonium atom, one alpha particle. Now, how many polonium atoms decay per second? 1.6 into 10 to the power 14. So, therefore, the number of alpha particles emitted, by 1.6 into 10 to the power 14 polonium atoms. One polonium atom, one alpha particle. Therefore, this much of polonium atoms, same number of alpha particles. So that is 1.6 into 10 to the power 14. So number of alpha particles emitted for 1 second is said to be the rate. So finally we can write, therefore the rate of emission. Therefore the rate of emission of alpha particles. Therefore the rate of emission of alpha particles is the same number, 1.6 into 10 to the power 14. The same number, 1.6 into 10 to the power 14. In the examination, if you write only the last statement, they will give you the full marks. Actually, the first and second statements are given for you to understand, but you no need to teach physics to the examiners in the examination. So directly write this equation in the exam, they will give you full marks. But now write them all, right? Now we are not doing an exam, we are learning. So now write them all. And I would like if somebody read all the 3 statements for all of us. We have written 3 statements on the board. Actually, I have written 3 statements. Somebody please read them all here. Then I'll be very happy.
Number of alpha particles given out due to a decay of a single polonium atom equal 1. Therefore, the number of alpha particles emitted equal 1.6 times 10 to the power 14. Therefore, the rate of emission of alpha particles equal 1.6 into 10 to the power 14.
Thank you, dear. Thank you very much. I would like to hear a voice of one more student. Please, one more student, please read all the statements here. One more student.
The number of alpha particles given out due to a decay of a single polonium atom equals 1. Therefore, the number of alpha particles emitted by 1.6 into 10 to the power 14 polonium atoms equals 1.6 into 10 to the power 14. Therefore, the rate of emission of alpha particles equals 1.6 into 10 to the power 14.
Very good. Thank you very much. Who wants more time to write the things, dear? Who wants more time to write the things? Anybody in the class? This is 14, right? Because some students can't see. This is 10 to the power 14. Who wants more time to write the things, dear? Shall we go to the next question? If you want any more time to write the things, just raise your hand. Okay, nobody wants time. So let's go to the next question. We are in Roman number 6. We have answered simple A of Roman number 6, simple B of Roman number 6, simple C of Roman number 6. Now we should answer simple D of Roman number 6. Somebody please read simple D question.
The initial rate of release of energy from the sample.
The initial rate of release energy from the sample. How much energy is released due to the decay of a single polonium atom here? We have calculated it here. We have calculated this. The amount of energy released due to the decay of a single polonium atom. We have found this. Somebody please tell me this value here. We have found it here.
(8.4 into 10 to the power minus 13).
Yeah, we have calculated it in previous questions. In the previous question, we have calculated this. I think you have said it correctly. Other students also please check whether his answer is the value given by the student is correct. The amount of energy released due to the decay of a single polonium atom is, as I remember, please tell me again here, 8.
So is it 8.24 into 10 to the power minus 11?
No, it's not the kinetic energy here. It is not the kinetic energy, the total energy released due to the decay of mass here. That's a reduction of
8.4
mass.
into 10 to the power minus 13, sir.
8.4 into
10 to the power minus 13.
10 to the power minus 13 joule. Please write this here. 8.4 into 10 to the power minus 13 joule. This is the amount of energy released due to the decay of a single polonium atom. What do the other students think here? Is this correct or wrong? This is the answer for simple C question. So we should write one more sentence for simple C. So if this is the amount of energy released due to the decay of a single polonium atom, right? So how much energy will be released due to the decay of how many atoms decay per second? We have found that value also. So therefore, the amount of energy. Therefore, the amount of energy released due to the decay of how many polonium atoms decay per second here? We found it. Number of polonium atoms decay per second. We have found it as 1.60 into 10 to the power 14. We have found this. So therefore, the amount of energy released due to the decay of this much of polonium atoms equals single atom will give us 8.4 into 10 to the power 8.4 into 10 to the power minus 30. That is the amount of energy given by one atom. Therefore, we want to find the amount of energy given by how many atoms here? Therefore, we should multiply this by 1.60 into 10 to the power 14. Can somebody multiply this and tell me the value here? amount of energy given out due to the decay of one polonium atom is 8.4 into 10 to the power minus 4. So now we want to find the amount of energy given out due to the decay of 1.6 into 10 to the power minus 4, 10 to the power 14 plus 14. Actually, we have found this value earlier. Please write this here. Please write the statements quick. If you have multiplied, please tell me the value here. So what is the energy released due to this much of this much when 1.60 into 10 to the power 14 atoms decay? Can you simplify and tell me the value?
1.344 into 10 to the power 2. 344
1.344 into 10 to the power. Right, I think your answer is correct. 8.4 multiplied by 1.60 into here 10 to the power minus 13, here 10 to the power plus 14. So 10 to the power minus 13 multiplied by 10 to the power plus 14 means 10 to the power plus 1. 10 to the power plus 1. So actually 10 to the power plus 1 means 10. So we have to multiply 8.4, 1.6 and 10. 10 to the power plus 1 means 10. So if we multiply all these numbers, we will get, let me check. I think the students who gave me the answer is correct. 8.4 should be multiplied by 1.6 and that should be multiplied by 10. So that is 134. 134.4 joules. So this much of energy is given out due to the decay of this much of atoms. Due to the decay of this much of atoms. Okay, dear. Now I please check whether this answer is correct. Now you can see everything clearly. Who got this answer? Anybody in the class? Now who got this answer? Right, but we should write one more statement. Therefore, we should write one more statement. Therefore, the initial rate of emission of energy. Therefore, the initial rate of emission of energy. Right? So initially this much of atoms broken per second. At the beginning 1.6 into 10 to the power 14 number of atoms are broken per second. Initially 1.6 into 10 to the power 14 number of atoms broken per second. Due to the broken of 1.6 into 10 to the power 14 number of atoms, 134.4 joules of energy is released. Therefore, the amount of energy released for 1 second is 134.4. Therefore, the rate of emission of energy is also that value. So that is 134.4 unit is joules per second. So do not forget to write the units, joules per second. Got it here? Is it clear for all? Lamai?
Yes, sir.
Right. Now I want you to do something for me. Wait. Now somebody unmute the mic and read the 3 statements that we have written. Somebody unmute the mic and read the 3 statements that we have written. Start there.
The amount of energy released due to the decay of a single polonium atom equals 8.4 into 10 to the power minus 13 joules. Therefore, the amount of energy released due to the decay of 1.6 into 10 to the power 14 equals 8.4 into 10 to the power minus 13 into 1.6 into 10 to the power 14 equals 134.4 joules per second. Therefore, the initial rate of emission of energy equals 134.4 joules per second.
Right, excellent dear. Thank you. I would like to hear the voice of another student. Please read all the 3 statements that we have written to obtain the answer for this question. One more student.
The amount of energy released due to the decay of single polonium atom is equal to 8.4 into 10 to the power 13 joules. Therefore, the amount of energy released due to the decay of 1.60 into 10 to the power 14 is equal to 8.4 into 10 to the power negative 13 into 1.60 into 10 to the power 14. Therefore, the initial rate of emission of energy is equal to 1.344 into 10 to the power 2 joules per second.
Very good, dear. Who would like if I explain the things again? Anybody? If anyone wants to explain this again, just raise your hand up, then I'll again explain. Anybody in the class? Who wants more time to write the things here? Because I'm going to erase everything. Who wants any more time to write the 3 statements? We have written 3 statements here. Yeah? If so, if you don't want any more time, let's go to the next question. Right. We should go to the next question. Right. Can somebody unmute the mic and read simple E question? Read simple E, quick.
the half-life T of polonium in days?
Thank you, dear. We want to find the half-life of polonium, not in days, but in seconds. They have given 1 second equal to how many days, dear? 1 second is equal to 1.16 into 10 to the power minus 5 days. So first of all, let's find the half-life in seconds. After that, we convert the seconds into days. I think that's much easier. So they have given the half-life equation. I don't like this, but they have given. It's better if professors stop giving the equations, because students must be able to remember at least few of the equations. Unfortunately, they have given this equation. It's not a good thing, right? We should explain what the half-life is. Before we go to that question, if you want any more time to write the things on this whiteboard, please take a screenshot. I'm going to erase everything that I have written on the whiteboard. Before we answer simple equation, if you want, please take a screenshot. I'm going to erase everything. What is half-life here? So if we have, for example, let's say we have 10 polonium atoms in a sample. So half-life means the time taken to be the half. It means if we have 10 polonium atoms, right? If we take 4 seconds to decay, reduce 10 polonium atoms into 5 polonium atoms, then 4 seconds is said to be the half-life. In a sample, we have 10 polonium atoms. Let's imagine. After 4 seconds, only 5 polonium atoms are there in the sample. It means 5 of the atoms have been broken, decayed. So then we say 4 seconds is the half-life. The time taken for the number of mother nuclei to be half is said to be the half-life. Right. So they have given us the equation to calculate half-life. So last week, as I remember, we have found the half-life equation, right? So half-life equation, they have given it as T equals 0.7 divided by lambda. Check. They have given this equation, and lambda is the decay constant. They have given us the decay constant at the they have given us the decay constant as 5.6 into 10 to the power minus 8. They have given the value of the decay constant as 5.6 into 10 to the power minus 8. So you should remember that this is given in seconds. The easiest way to simplify is I'll take 1 decimal point to this side and 1 decimal point from this number. So then it will be 7 over 56. 10 to the power minus 8 comes up as 10 to the power plus 8. 7 over 6 into 10 to the power plus 8 is the half-life, or the time taken for the number of polonium atoms to be half. 7 divided by 7 is 1. 56 divided by 7 is 8. 1 into 8 into 10 to the power plus 8 seconds is the half-life. But we have to convert seconds into days. First of all, you write them. After that, let's try to convert the half-life, the units of half-life seconds to days. Start. Write them there.
Sir. Excuse me, sir. Sir, are you there?
Did you ask anything, Sia? I didn't hear you.
No, sir, it got solved out.
Okay, sorry. Sometimes I can't hear because I'm using my laptop's speakers. Sometimes they do not work properly. Right? If I do not answer when you ask a question, if I do not answer your question, please ask it 2-3 times. Sorry.
It's okay, sir.
Right. Here it is given that I think you all will hear me. 1 second is equal to how many days? Somebody unmute the mic and tell me. 1 second is equal to how many days here? Somebody in the class, please tell me. Unmute the mic and tell me the relationship between 1 seconds and days. Please don't waste the time.
One second equals 1.16 into 10 to the power minus 5 days.
Very good. It's given in the question that 1 second equal to 1.16 into 10 to the power minus 5 days. So here we have this much of seconds. Here we have this much of seconds. So 1 second equals to 1.16 into 10 to the power. Don't remember the value. 1 second equal 1.16 into 10 to the power minus 5 days. 10 to the power minus 5. Now unit will be days. So this much of seconds should be equal to 1.8 into 10 to the power 8 multiplied by this. Then we can convert the seconds into days. Then we can convert seconds into days. So what will be the final answer? How do we convert this? Plus 8 minus 5. That's so simple. That is 10 to the power 3. Let's divide here. 1 divided by 8 is 0. 1 and 1, 11. 11 divided by 8 is 1. 3 remaining. 36 divided by 8. 36 divided by 8 is 4. 32. Then 4 remaining. 40 divided by 8 is 5. Into 10 to the power 8. 10 to the power minus 5 means 10 to the power plus 3. Unit is days. So 10 to the power plus 3 means 1000. 1000 into 0.145 means 145 days. So what is the half-life of polonium in days, dear? 145. Who got this answer? Who got this answer earlier? Anybody in the class? Right. Who wants more time to write? Shall we go to the next question? Shall we go to the next question? Who wants more time to write the things? Okay, I'll show you the next question. Right. Somebody unmute the mic and read simple F question. Do not waste the time. Quickly read simple F question.
Approximately by what fraction does the activity of a given polonium sample decrease in 2 years?
Thank you, dear. Thank you very much. Would you please read one more time, dear? Loudly, please.
Yes, sir. Approximately by what fraction does the activity of a given polonium sample decrease in 2 years?
Thank you, dear. Approximately by what fraction does the activity of a given polonium sample decreases in 2 years? It's keyword, right? Right. We have found the half-life of polonium. 2 years mean how many days, dear? 2 years means how many days? Am I? 2 years. We have found the initial activity. I don't remember, but we have found it. 2 years means how many days, dear? Somebody in the class? Right. How many years for one? How many days for 1 year, dear?
365.
Very good. 1 year, very good. Equals 365 days. So 2 years means 365 should be multiplied by 2. Am I right here? So what is the half-life of polonium? Half-life of polonium, 145 days. So can you tell me, therefore, the number of half-lives completed by polonium within 2 years. Within 2 years. How do we find this year? Somebody please tell me. What should I do to find the number of half-lives completed by polonium for 2 years? What should I do?
Multiply 365 by 2 and divide the answer by 145.
Very good. Very good. Would you please tell again?
Multiply 365 by 2 and divide the answer by 145.
Very good. Excellent. Excellent. This is the number of days. 365 times 365. 365 multiplied by 2 is the number of days that we kept the sample. This is the number of days. We should divide by the half-life. The number of days, half-life is 145 days. So what is the easiest method to simplify here? 36 divided by 5 is 5 times 7, 35, 1 remaining. 15 divided by 5 is 3, 73. 14 divided by 5 is 2, 10, 4 remain. 45 divided by 5 is 9, 29 into 2. Can you divide this and tell me the value here? 73 and 29. Can we divide it? No, can't. So 3 times 2 is 6. 7 times 2, 14. 146 divided by 29. Somebody please divide this and tell me the number of half-lives completed by polonium within 2 years. Write them all and give me the value here. Start. If we divide this, we will get 5.03 approximately. 5.03 half-lives. 5.03 can be written approximately 5. So how many half-lives completed by polonium for 2 years here? Polonium will complete approximately 5 half-lives. You can neglect this 0.3. It's not such a big thing. Who got this answer like 5.030 as 5? Who got this? Lamai? What does it mean there? What's the meaning that polonium has I have muted? No, I have unmuted. Right. What's the meaning that polonium has completed 5 half-lives? What does it mean there? At once we can get the answer by using an equation, but I don't want to use the equation directly. I want to explain this. I want to revise the knowledge, because you have to sit for the exam, you have to revise the things, you should remember the things. So it's better to revise. Meaning that this atom has completed this polonium has completed 5 half-lives, mean something like this. Let's say there are n number of polonium atoms in the sample at the beginning. After one half-life, HL for half-life, there will be n over 2 number of atoms in the sample. At the beginning, if we have n number of atoms in the sample, after one half-life, there will be n over 2. If we wait, if we allow the polonium to complete another half-life, then n over 2 should be divided by 2. This will be half. N over 2 into half means n over 4. This will be n over 4 after 2 half-lives. If we wait, if we allow the polonium to complete another half-life, right? Then n over 4 will be reduced by, n over 4 is the number of polonium atoms. N over 4 will be reduced by half. So it will be n over 8. If we allow polonium to complete another half-life, so there will be n over 8 should be reduced by 2. It means it will be n over 16. 1, 2, 3, 4. We want one more half-life. If we allow polonium to complete one more half-life, this will be n over 16 will be reduced by half. So it will be n over 32. So how many polonium atoms will be in the sample after 5 half-lives, dear? Somebody unmute the mic and tell me. If the initial number of polonium atoms is n, after 5 half-lives, how many polonium atoms will be in the sample? Somebody unmute the mic and tell me.
N over 32.
N over 32. N over 32. But that's an equation to obtain this n over 32 value at once. What is that equation here? So we can write the initial number of polonium atoms in the sample. The initial number of polonium atoms in the sample. In the sample mean we have to keep somewhere else, right? Maybe in a bottle or anything. Initial number of polonium atoms in the sample, let's say n. Then what will be, therefore, the number of polonium atoms in the same sample after 5 half-lives. That's an equation to find this. What is the equation here? That's the equation to find directly n over 32. What is that equation? Somebody please tell me here.
E to the power minus lambda t dot n.
No dear, that's a very simple equation. We write n divided by something. Initial number of polonium
N over
atoms
2
in the
to the power
sample
n.
is capital N. I want to find the number of polonium atoms in sample after completing 5 half-lives. That's a very simple equation. What is it?
N over 2 to the power 5.
N into 10 to the power, very good. N divided by 2 to the power 5. 2 to the power number of half-lives that which was completed. 2 to the power 5 means 2, 4, 8, 16, 32. So 2 to the power 5 means 32. So this is the method. So I have written both methods that can be used to find the number of polonium atoms in the sample after completing 5 half-lives. But I would like if you write both methods and in the examination use only the equation method. Okay, dear? Start. Use only this method in the examination But now you write both steps, both methods, quick. Write them all. Let me read the question once again. Simple left question. Approximately by what fraction does the activity of a given polonium sample decreases in 2 years? Approximately by what fraction does the activity of a given polonium sample decreases in 2 years? So let's try to find it here. We want to find the decrease of activity, the decrease of activity for 2 years. So it's better write the fraction of the fractional decrease of activity for 2 years. It's better write like this. So the decrease of activity for 2 years is equals initial activity minus initial activity minus final activity. Final activity divided by initial activity. Divided by initial activity. Please write the equation here. The fractional decrease of activity, the fractional decrease of activity equals initial activity minus final activity divided by initial activity. Write the equation here quick. The fractional decrease of activity equals initial activity minus final activity divided by time taken Right, initial activity can be indicated as A1. Final activity can be indicated as A2 divided by initial activity A1. Activity is given by the equation A equals lambda n. We have proved it. Activity equals activity capital A equals lambda times n. We have proved it already. So initial activity lambda times n1. Final activity lambda times n, here n is n2, divided by initial activity lambda n1. Now you should understand that lambda, all the lambda terms are cancelled out. There will only be n terms, n1 minus n2 divided by n1. Can you do the rest and tell me the final answer? And this is the final question of this past page. Complete and tell me the answer right here. Who has simplified this dear? Anybody in the class? The
0.96.
fractional decrease of activity for 2 years equals n1 minus n2 divided by n1. N1 is the number of polonium atoms in the sample at the beginning. N2 is the number of polonium atoms in the same sample after 2 years. N1 is N, N2 is N over 32. N2 is N over 32. Divided by N1 is again capital N. That's how we simplify. I think you have written this part. But if you want any more time to write this, please take a screenshot. If you want to write this any more time, if you want to write it, please take a screenshot. I'm going to erase it. Right. Now, how do we simplify it here? I'll take 32 as the common denominator for n over 32 and n. So this n should be multiplied by 32. Once this n is multiplied by 32, nothing will happen to this n. This is the 32 is the common denominator divided by n. So that's it. That is this n divided by n. Now here we have 32 times n minus n divided by 32 divided by n. 32 minus 1. 32 minus 1 is 31. 31n divided by 32. The division becomes multiplication when you take the reciprocal. This division will be multiplication when you get the reciprocal of capital N. So that will be 1 over capital N. Now this N and this N cancelled out. Finally, you get the answer as 31 over 32. What's the final answer there? 31 over 32. If you can't see it, let me write here. The final answer is 31 over 32. 31 over 32. Who got this answer? Anybody in the class? The fractional decrease of activity is 31 over 32. Who got this? Come on. If you divide this, you will get approximately, this is approximately equal 0.97. It means its activity is highly reduced. Right. So as this is an examination question, you have to divide this in the exam. So in modern days, we use the energy reached by this kind of a nuclear reaction to generate electricity. So they are such power plants are known as nuclear power plants. But at the beginning of this science, humans use the nuclear power to make bombs. So that's not good. I think you have heard about Hiroshima and Nagasaki. So normally humans, first of all, they used to destroy things. After that, they use the new technology science for the good. But first they use it for the bad. So that's the nature of humans. Right. And there are two terms which are known as fusion and fission. Have you heard them here? Have you heard, please write them first. Have you heard those words? Have you heard the two words, fusion and fission? Fusion and fission. Come on. So you may have not. Is there even a single student who has heard the terms fusion and fission?
Yes, sir.
You have heard. Very good. So what is the meaning of fission here? Fission means nuclear fission means this. So the previous nuclear reaction, polonium 210 broken into lead and alpha. It's broken into two pieces. This is known as fission. Polonium atom broken into two pieces as lead and another particle. Fusion means atoms are combined together. For example, 4 hydrogen atoms combine together and make helium atom. So this is what happened in our star, sun. So that's the meaning of fission and fusion. In the fission, a single atom is broken, split into several other atoms and particles. In fusion, atoms are combined together and make a single atom. Clear? Oneness. Sorry, there should be only oneness fusion. So please write the next subheading: fission and fusion. Please write the next subheading: fission and fusion. Fission and fusion. Right? And write these two things. Write the heading as fission and fusion. Then write them. Then please write them, because you need a small understand about this. And somebody unmute the mic and tell me which is the method, fission or fusion, that we use to generate electricity in nuclear power plants. Fission or fusion? Somebody please tell me. Unmute the mic and tell me. What is the method that we
Fission.
use? Yes, Damidu. Yes, Damidu, please tell me.
Fission.
Speak loudly, dear, please.
Fission.
Yes, in nuclear power plants, we use in humans. As humans, we cannot make fusion. We make fission. It means we break some atoms into other kinds of atoms and particles. So that's the problem. Due to the fission, some harmful things are generated. But if we are able to use fusion, nothing, no harmful things are generated. But unfortunately, we can't generate. Still, we have not. It means laboratories, we are able to do the things in labs. But in practice, in a power plant, still we are not able to use fusion. If it is possible, if fusion is possible, we have a lot of energy on the earth. How? If this is possible for us, if fusion is possible for us, energy will be the cheapest thing on the earth. Why? Can somebody explain? Lamai?
Using seawater for fusion.
Yes, we have a lot of water. We have a lot of water. One water molecule has 2 hydrogen atoms. So it's very easy to, by using electricity, we can break this H2O molecule into hydrogen and oxygen. Oxygen can be used in so many industries, and hydrogen can be used in fusion. Then we can generate energy. This energy will be almost free. So when you go to university, try to find a cheap and easier method for fusion, nuclear fusion. You will try when you in university, not now, right? First of all, pass the advanced level. Go to university. At university, you may have more than enough free time. So then you will try to find a method for fusion. Okay, so please try. In nuclear fission, heavy atoms heavy atoms are broken into lighter atoms. In nuclear fission, heavy atoms are broken into lighter atoms. Lighter atoms. Full stop. In nuclear fusion, several lighter atoms combine together to make a heavier atom. In nuclear fusion, several lighter atoms combine together to make a heavier atom. In heavier atom. Full stop. Right. Star point and right. Nuclear fission is the method we use to generate electrical energy, electricity in nuclear power plant. Nuclear fission is the method we use to generate electricity in nuclear power plants. Right? So sometimes in nuclear power plants, they will generate some harmful particles and harmful radiations. But if it is possible for the fusion, it will be cheap and safe. Right. The other star point, one more star point. The sun generates energy by nuclear fusion. The sun generates electrical energy by nuclear fusion. Right. Somebody please unmute the mic and read the note that I have given under fission and fusion, including the star points. Read them all quick.
Last sentence.
The sun generates energy. The last star point. The sun generates energy by nuclear fusion. Right. Somebody read all the things.
In nuclear fission, heavy atoms are broken into lighter atoms. In nuclear fusion, several lighter atoms combine together to make a heavier atom. Nuclear fission is the method we use to generate electricity in nuclear power plants. The sun generates energy by nuclear fusion.
Right. Thank you, dear. Shall we go to next? The water can easily be obtained from ocean here. The ocean is full of water. Right? We can easily obtain water from the ocean. No need to cut trees, no need to take water from rivers. For the nuclear fusion, if you want hydrogen, it's easiest way to take water from ocean. Right. Shall we go to the next question? I think you have heard that. If you search in the internet about Saudi Arabia and Israel, they take water from sea and they use a process called reverse osmosis. Who has heard reverse osmosis? By using that method, they convert salt water into drinkable water. Search them. So by using that method, we can easily obtain as much as water that we want. So simple, right? Search them, and there are so many technologies to convert seawater into pure clean water without any other particles. Only H2O will be there. Search. You'll be there are two wonderful projects I have seen. One in Israel, the other one in Saudi Arabia. Just check them here. Right, shall we go to the next question here? Shall we go to another past paper question, Lamai? Are you tired there? Okay, please read all the points that I have given under fission and fusion. Somebody please read everything that I have given under fission and fusion. Then let's decide whether to discuss. Let's discuss. Somebody please read everything here that I have given under fission and fusion once again, one more time.
In nuclear fission, heavy atoms are broken into lighter atoms. In nuclear fusion, several lighter atoms are combined together to make a heavy atom. Nuclear fission is the method we use to generate electricity in nuclear power plants. The sun generates electrical energy by nuclear fusion.
Right. I'll show you one more past paper question. Let's get a start and you may play the rest at home. Let's try to get a start. You may try to complete the rest at home. This question was given in 2009. This was given in 2009. That question was given with a huge paragraph. So please write the heading as 2009 AL and read the paragraph. Somebody unmute the mic and read the paragraph. Start. Why are you wasting time? Do you want to wait another half an hour with me? Read the paragraph
Sir.
loudly.
The sun, which provides the energy necessary to sustain all forms of life on the earth, is a star in our galaxy. At present, the sun contains about 74% of hydrogen and 24% of helium by mass, and remaining 2% makes up same of the heavier elements. All these elements are in a completely ionized gaseous state, also known as a plasma state. The photosphere is the lowest of the three layers comprising the sun's atmosphere and has a black body spectrum. Most of the visible light from the sun comes from this photosphere, which has a relatively small thickness. Immediately above the photosphere, there is a dim layer of less dense gas called the chromosphere. The outermost region of the sun's atmosphere, the corona, extends several million kilometers from the chromosphere. Because the corona is the furthest region in the sun's atmosphere from the surface of the sun, it is expected that temperature in that region to be the lowest, but it has been found that the highest temperature of the sun's atmosphere, which is around 1.5 times 10 to the power 6 Kelvin, sorry, 1.5 times 10 to the power 6 is in the coronal region. Astrophysicists have suggested that this unexpected rise in temperature of the corona is due to the release of energy carried from the interior of the sun by complex magnetic fields that exist in the sun. Region below the photosphere is considered to be the interior of the sun and has a radius of 7 into 10 to the power 5 meters, which is also considered as the solar radius, and a mass m equal 10 to the power 2 to the power 10 to the sorry, 2 times 10 to the power 30 kilogram. The region closer to the center of the sun, where the temperature and pressure are very high, is known as the core. Because of very high temperature and pressure, fusion of hydrogen nuclei takes place at the core of the sun. This hydrogen fusion reaction can be written as follows. 4H gives helium plus 2 electron plus neutrons plus energy. The generated energy travels to the surface of the sun and is released from there. When answered in the following questions, take Wien's constant to be 3 times 10 to the power negative 3 meters Kelvin.
Right, thank you, dear. This is Wien's constant. You may have not heard it, but I write Wien's constant. Thank you, dear. Right, you will learn about Wien's constant later. 2009 matter radiation equation. What is meant by plasma state of matter? What does it mean, dear? Please start. Please write the heading 2009 AL matter and radiation equation. 2009 AL matter and radiation essay equation. Right, let's do word 5. Okay, what is meant by plasma state? What is meant by plasma state here? So if you go to this paragraph, they have given us a huge paragraph. In the paragraph, we found that somewhere else. Where is it? In the first paragraph, do we have the term plasma? Check.
Ionized gaseous state, also known as plasma.
Where is it here? In the first paragraph or second paragraph or third paragraph? I just want to highlight it.
First paragraph, last line.
All the elements are completely ionized. Gaseous state, also known as plasma state. Very good, dear. So this answer is directly given in the question. You see, all these elements, when all the elements are in a completely ionized gaseous state, then that is known as plasma state. That's the answer. That's the answer for the first question. So let's write it there. Let's write the answer for, is it Roman number 1? What's the answer? What is meant by the plasma state of matter? So answer is here. What is meant by plasma state of matter? Let's write it. Let's write the answer. Answer is when all the elements are in the complete ionized gaseous state, comma, that is known as plasma state. So this is the answer for Roman number 1. Okay, dear? Everybody please write this here. For Roman number 1, this is the answer. Everybody please write answer for Roman number 1. When all the elements are in the complete ionized gaseous state, that is known as plasma state. It means, are there atoms here? Are there atoms? Somebody please tell me. Lamai, are there atoms in a plasma state? It is clearly saying that all them are ionized. Ionized means no atoms. Ions are not called atoms here. Positive ions, negative ions. Are there liquids? Are there liquids in plasma state? Lamai? Lamai, are there liquids in the plasma state?
No.
No.
No, because it said everything is in the gaseous state. All the things are behaves very similar to a gaseous state. Therefore, no liquids, no solids. All the things will be very similar to gas, but all they are ionized. There are no atoms. So all the things will be positive and negative ions. Right. Now let's go to Roman number 2. I think you have written. Let's go to Roman number 2. Right, so this is the answer for Roman number 1. Somebody please read. Somebody please read Roman number 2.
What are the three regions exist in the sun's atmosphere?
What are the 3 regions exist in the sun's atmosphere? What are the 3 regions here? They are clearly given here. So this is the answer for Roman number 1. If you read the paragraph, you can easily find the 3 regions exist in the sun's atmosphere. We can easily find. Let's go to the paragraph and let's try to find. Where can we find? In the first paragraph, no. What about second and third paragraph?
Second and third.
What are they here?
Photosphere, chromosphere, and corona.
Where are they? Are they in the third paragraph? No, second paragraph. The visible light comes from this photosphere, which is relatively smaller thickness. Yes, can you highlight? Yeah, I like that method. Photosphere. Photosphere is there. Chromosphere and corona. Right, very good. So what's the answer for Roman number 3? Sorry, Roman number 2. There are 3 regions. The first one is the photosphere. Very good. Is the photosphere. Second one, Lamai. What is the second region?
Chromosphere.
Chromosphere. Right? Very good. Very good. Chromosphere. Third one, everything should be extracted from the paragraph figure because these things are not in the syllabus. That's why they have given us a paragraph. If those things are in our syllabus, they will not give us a paragraph. So what is the third one here? Corona, right? Third one is corona. Not this corona. Right. Please write the answer for Roman number 2, dear. Please write the answer for Roman number 2. Right, now let's go to Roman number 3. Let's go to Roman number 3. Right, somebody unmute the mic and read Roman number 3, quick. Somebody unmute the mic and read Roman number 3.
What region of the sun's atmosphere has the highest temperature? Give reasons for that region to have highest temperature.
Very good. Which region of the sun, of the atmosphere, which region of the sun's atmosphere has the highest temperature? Give the reason for it. Give the reason. So they ask the reasons also. So reasons. Give the reasons for that region to have highest temperature. So let's go there. Let's go. Right. Where can we find that? Somebody, you will try. You can highlight and show me. Here, yes, very good. Thank you, Dasnika. But it has been found that highest temperature of the sun's atmosphere, which is around 1.5 into 10 to the power 6 Kelvin, is in the coronal region. It means corona region. The highest temperature is there in the corona region. Corona region. They asked us to give the reason also. Astrophysics, it means scientists who has learned a lot of things about astrology, right? So not astrology, the universal objects, stars, suns, comets, and those things. Astrophysics have suggested that this unexpected rise in temperature of the corona is due to the release of energy. We have to go to one more line below. Right. So what's the reason there? Scientists had given us the reason. Can you read the reason? Now you are able to see the reason. Lamai?
Due to the release of energy carried from the interior of the sun.
Yes, so that's directly given in the question paragraph, because these things are not in our syllabus. That's why they have given us a paragraph to find the answer. Let's just copy paste. Right, so astrophysics suggested that unexpected rise in temperature, this high temperature is due to the, can somebody underline, highlight and show it to me? Due to the release. Somebody underline that sentence here. Due to the release of energy. Thank you. Carried out. Due to the release of energy carried out from the interior. From the interior of the sun by, that's the last few words are the most important, by complex magnetic field that exist in the sun. By the complex magnetic fields that exist in the sun. So it's a very, if you do a research degree, MPhil or a PhD, it's better to study about these complex magnetic fields. It will consume a lot of time, but it will make you a great scientist if you have any time and if you have a wish to be a scientist. So let's write the answer. By complex magnetic fields, that exist in the sun. So that's the answer for Roman number 3. Please write them all here. Please write the answers for Roman number 1, 2, and 3. Start. Right, you may try to answer the rest of the questions at home. If you have written them,